to the PSGD committee for the opportunity to share this work with a wider audience today. So just go ahead and get started here. What I'd like to show you today is essentially a case study of deep injection-induced seismicity in the Delaware Basin of Texas and New Mexico. And I chose this particular case study because the region that we'll talk about is one of the most seismically active places, certainly in the mid-continent of the US, but actually probably in the US in general at the moment. This work draws on a lot of research from our team, the Center for Injection and Seismicity Research, or CISR, and you can see my co-authors listed there who have varied ranges of expertise. And this is really an integrated mechanistic analysis to understand induced seismicity caused by deep injection. So our program, CISR, partners with TexNet, which is funded by the state of Texas to monitor, catalog, and analyze earthquakes. They have a backbone of seismic stations across the state, and you can get a sense of that in the map on the right, as well as portable stations for particular areas of interest. And oops, I moved on. What CISR is an industrial associates program where we partner with sponsoring companies, 27 of whom you can see listed at the bottom of the slide there. And what their funding allows us to do is to broaden and deepen the portfolio of research that we can do using this high quality earthquake data, and allowing us to dive a bit more deeply to understand causality and to provide some tools that might enable mitigation. So induced seismicity in Texas has a history that predates even TexNet, which was put online in January of 2017 and started monitoring earthquakes then. But we can look at the history of seismicity in Texas at a magnitude 3 with relatively uniform regional detectability from about the year 2000 on. And that's what you see in the plot on the bottom left. What we're doing is tracking cumulative number of earthquakes in different areas of Texas, and you can see those areas outlined in the map on the right. So seismicity in Texas comes in different geologic habitats. And our work really started in the Fort Worth Basin, outlined in blue. These earthquakes were important because they were early on in the induced seismicity research program in about 2015 and 16, and because many of them occurred near the Dallas-Fort Worth metroplex, so they were of great concern societally as well. This is a relatively simple case of a foreland basin with injection above basement, so it was a nice initial research portfolio for our group. We've also looked at induced seismicity in the Eagleford region, which is a passive margin, and the seismicity there is caused almost exclusively by hydraulic fracturing and was relatively easy to mitigate with changes in operational practices. But the region I'd like to talk to you about today is in far west Texas and southeast New Mexico, and it's called the Permian Basin region, which is really comprised of two subbasins, the Delaware subbasin, which is outlined in yellow, and the Midland in the east is outlined in orange. And you can see that these two basins make up most of the earthquakes that are being recorded by TexNet today, including some pretty large magnitude events. And the Delaware Basin in particular, where we'll focus, is quite complex. It's structurally and geologically complex, but also has a pretty complex operational history with lots of hydraulic fracturing, older vertical production, more conventional production, and deep and shallow injection. You can see that the Delaware Basin is making up most of the earthquakes that we're seeing in Texas today. I did want to highlight, and this is important for our program and for induced seismicity in general, the black dots that you see on this chart are the annual Did You Feel It earthquakes recorded by USGS. So these are the unique number of events that are felt by the general public. And this is perhaps even of more concern than the number of earthquakes in general, because it gives us an idea of how much the public is feeling and how aware they are of earthquakes. And that's really the number that our program, along with our industry partners, works to mitigate down. So if we focus on the Permian Basin, what I'd like to do is talk a little bit about seismicity and operational influences, and then I'll dive pretty deeply into the geology and talk about our integrated research program here in the Delaware Basin. and get to some more mechanistic analyses toward the end of the talk. But starting just with the earthquakes, you can see those mapped in the map on the right, again with the Delaware and Midland Basin separated by this basement core central basin platform uplifted. The earthquakes are sized and shaded by magnitude, and what you see is about 2,000 earthquakes of magnitude 2 and above in the Delaware Basin, and about 500 in the Midland Basin. And these earthquakes fall into distinct geologic habitats. The larger magnitude events in the northern part of the Delaware Basin occur almost exclusively in crystalline basement, below the basement sediment interface, as opposed to earthquakes in the southern part of the basin, that many of which fall in the shallow sedimentary section. And so what I want to do is look at these earthquakes in the context of operations in the basin before I dive into geology. And so the horizontal wells in the basin, of which there are about 35,000, so it's a pretty heavily developed basin or region in general, are shown as blue squares or circles, and these are sized by the volume of fluid produced. But of more importance in this basin is the volume of fluid that's re-injected. So for every barrel of oil we have produced, we have 2 or 3 or sometimes 5 times that volume of water. And the main way that that water is dealt with is by re-injection into strata that are shallower or deeper than the shale producing intervals. So this is injection for permanent disposal. It's not EOR or those types of operations. This is just putting water underground permanently for disposal. And you can see in the cross section on the left, which is really a smash section, we call it, it contains all the data from the basin pushed onto one cross section. So there's obviously a lot of depth variability that creates noise here. But what I'd like you to see is these trends in earthquakes relative to operations. We have this region in the northwestern Delaware Basin we call the Culberson-Mentone earthquake zone. These earthquakes occur in the basement, and there are a lot of them. That's this area outlined by the black dashed line. And these are some large magnitude events that I'll talk about in just a moment. And this is in contrast to the shallower events occurring in the sedimentary section above the basement sediment interface in the southern part of the basin. And as I said, in the Midland Basin, these earthquakes are deep in the basement, and are the most proximal operational influence for these is deep injection into carbonates sitting right above basement. In terms of the rates of earthquakes and operations, what you can see that is deep injection plotted as a purple line for both basins here, Delaware on the left, Midland on the right. Deep injection is occurring at about 50 million barrels per month in both basins. Shallow injection volumetrically is much more important in the Delaware Basin than deep is in either basin. Earthquake rates in the Delaware Basin have gone up to about 200 of magnitude 2 and above per month. In the Midland Basin, we've seen earthquake rates plateau since about 2021 or so. So if we zoom in just in the Delaware Basin, where we'll spend most of our time today, starting to look at the geology of these injection strata. So shallow injection is occurring mainly in the southern portion of the basin. You can see that it actually trends with the Texas-New Mexico state line here. And there's a regulatory reason for that, with New Mexico not allowing much shallow injection in recent years. That injection is going into dominantly sandstones, turbidite sands of Guadalupean age called the Delaware Mountain Group. And this is in contrast to the deep injection, which takes place into mainly Silurian and Devonian carbonates, some Ordovician age disposal as well. And that's concentrated in the northern part of the basin. And as I said, this earthquake region we have particular interest in is the Culberson-Mentone earthquake zone. You can see the density of events there, and these are again sized and shaded by magnitude. But we have some appreciable seismicity in New Mexico as well. And we can look at a few of these important events. There was a magnitude 4 on the Eddy Lee County line in New Mexico, the magnitude 4.9 Mentone event, which was in 2020. On the Culberson-Reeves County line in Texas. And then recently, November of last year, we had the magnitude 5.4 Coalson event, which is shown here. One important thing that I want to note here is that these earthquakes in many cases are quite distal from deep injection. So on the order of 20 kilometers or so from the nearest deep injection well. However, they are occurring exclusively in the basement on basement-rooted faults. And so deep injection is like the likely cause, or our hypothesis going into this study. So I'll talk a bit more about geology now. The structural interpretation work relies heavily on the work of my colleague Lily Horn, who's published several papers on this region. And let's start from the bottom up. The basement in this area, the Delaware Basin is outlined in a solid black line here, is extremely complex. So we're already starting with complexity from the bottom up. There are several different basement lithologies observed, including mafic complexes. And importantly, there's a pretty major plate boundary or suture zone, the Grenville Front, which bisects this basin. So there's a lot going on already from the basement. The deep injection strata, the carbonates, are deformed by basement-rooted reverse faults. So some of these are the large faults that actually form the structure of the basin when you think of the Delaware Basin transitioning to the Central Basin platform. So those are the types of faults we're talking about. And you can see those in the schematic or the cross-section up above. So these faults are interpreted by Lilly and others to tip out largely in the Pennsylvanian and to not really extend very far into the shale producing intervals of Wolfcampian and certainly Leonardian age. These faults are kinematically decoupled probably from the another set of faults which are shallow, and these shallow faults are in the Delaware Mountain group, the shallow injection strata. So these are the faults that the shallow earthquakes are hosted on. As I said, magnitudes are a bit smaller here with a magnitude ceiling of about 3.5. And that's likely because these faults are smaller. They are cutting less stiff strata, and they're strata bound essentially to those shallow injection intervals. So for the rest of the talk, when we talk about faults and we talk about geology, we're talking about these deep injection intervals primarily, with basement rooted faults that are slipping in a normal sense today and cut through the deep injection strata. What we've done then is build a pretty detailed geologic model. We have the structural interpretation from the team, and now we look at the deep injection strata themselves. So what are their structure and thicknesses and reservoir properties? And this will eventually populate a 3D geocellular model and a pore pressure model that allows us to map pore pressure and stress changes, model and map pore pressure and stress changes that we can then integrate with our fault interpretation. So what I'm showing here are just three horizons of interpretation. From the top down, our model domain is cut at the top at the base of the Wolfcamp Formation in the Pennsylvanian. And you can see we have a lot of nice well control there in the Wolfcamp. So this is really the top of deep injection strata for us. We have an important marker at the base of the Woodford Formation, and you can see that Siluro-Devonian elevation map here enlarged in the middle, because that brackets the top of our deep injection strata, which are these carbonates of Silurian and Devonian age and Ordovician age in part. So that's where most of our injection is occurring. And then we have a new basement map, which will be published hopefully later this year, focusing just on Texas. And you can see the basement elevation there on the left. Very little well control here to understand basement, despite its importance here for induced seismicity in the basement. What I want you to see in the structure maps of each of these is that there are a lot of similarities. And one of the really important things here that's bounding the southern boundary of our model is the east-west trending Grisham fault zone. This is really a series of faults that completely offset our injection intervals in places. And so our model domain is bounded on the south by the Grisham fault zone. We extend onto the northwest shelf, quite distal from deep injection. We bound on the east by the Central Basin platform, where these units are of course offset. And then on the west, we're again quite distal from deep injection. Here are just some thickness maps of some of our main injection strata. I won't spend too much time on this, but I want you to see the differences in our depot centers. The Ordovician age thicknesses really represent a Tobosa Basin, that initial subsidence of the platform on which these carbonates were deposited. It looks quite different from the Silurian and Devonian, and I'll talk about this in just a minute. That's our main injection interval. And of course, the Pennsylvanian has this really strong structural control with the being a syntectonic a unit, Pennsylvanian age, with the east-west trending Grisham Fault Zone bounding our Pennsylvanian unit thickness. Now, I talked a bit about the importance of basement, but this goes even into our geologic interpretation of the Silurian and Devonian age units, because what we have noted is that the ancestral Silurian platform margin, which dictates whether we have dolomitized platform carbonates to the north or basinal limestone and chert to the south, that the position of that platform margin, it seems to be trending with the Granville front. So we have this inherited crustal weakness that is then controlling the deposition of our carbonates to the north and south of that platform boundary. And so it's really quite important, really, that we have an understanding of the basement as it controls even what we see in Silurian and Devonian. And this trend, we think, extends into the Midland Basin as well. And you can see an image here where we're interpreting the main types of deposition across the Permian Basin in general. Now, when we go to interpret reservoir properties for our flow model, when we model the flow of injected fluid, one of the things that's really important is understanding porosity and permeability. And this is a challenge in these carbonate systems. So we take all available wells where we have high quality log suites and interpret mineral volumes and porosity, as well as giving a simplified rock type. Is it a limestone or dolomite? And these rock types are critical in our 3D geocellular model to control how we distribute permeability and porosity. You can see that from our log interpretation, porosities are very low. Even in dolomites, they're on the order of 2 to 3%. And this is consistent with what's seen in core data. We don't have a lot of core data, but we expand to take data from carbonates, deep carbonates across the whole Permian Basin. And what we see is that even at low porosities of 4 to 5%, we have higher permeabilities that can be predicted by standard porosity permeability relationships. And that's because these rocks are have permeability that's highly enhanced by fractures. And this is just inherently difficult to model when we talk about modeling pore pressures and pressure distributions. And I'll talk a little bit later about how we work around this in our pore pressure model. So with this detailed geologic characterization, we build a 3D geocellular model, and an image of that is on the left. This is work by my colleague Amanda Kaye. This is a non-faulted model where she builds in formation surfaces and isocores, distributes lithofacies or lithologies, and matrix porosity and permeability. And that model is then upscaled into a CMG stars flow model. And you can see a cross section here. This is along the southern boundary of the model, so essentially the Grisham Fault Zone, and showing the distribution of matrix porosity. Porosity is highest toward the top of our model, which is consistent with those Pennsylvanian aged shales that have a little bit more siliciclastic material and higher porosity and permeability. In the CMG stars flow model, we have 10 model layers from Pennsylvanian into basement, and just over 250,000 cells with an average vertical cell size of 337 feet. So I talked about the challenge with matrix permeability in these systems, and especially with the fracture dominated flow systems. One of the ways that our flow modelers are able to work around this is to take field data, injectivity and field permeability data, to get a sense of what the permeability fields are actually in the subsurface. And so this is work by June Ga and JP Nico. And what they're able to do is to globally modify or calibrate the permeability field to match with what's observed in real data. And you can see an example on the bottom here of modeled bottom hole pressure in MPa on the left versus field bottom hole pressure on the bottom. And there's a lot of detail that goes into how they take wellhead flowing pressures to get bottom hole pressures. But what you can see is quite a nice correlation here between the the bottom hole pressures that are being modeled versus what's being observed in the field. So that's the calibration work simplified for the pore pressure model. Now I'll jump straight to some results here. I've got quite a few slides on results, but I want to leave plenty of time for questions. So what I'm showing now is the pore pressure evolution with deep injection. So modeling actual injection wells with the perforated intervals put into our CMG stars model. And the pore pressure maps here are actually change in pore pressure from 1983 to January of the year that we're listing. And so you can see how pore pressure is increasing over time. And on these maps, I've also placed the earthquakes. New Mexico Tech earthquakes are shown in pink, just north of the state line, and TexNet earthquakes in yellow. And the most recent earthquakes are the ones that appear dark. So dark pink in New Mexico and dark orange in Texas. If you remember from earlier in the talk, I said that some of these earthquakes, especially lower magnitude earthquakes in the south, are caused by shallow injection in part, and in some cases by hydraulic fracturing. And so these are outside our model domain. We have a separate shallow pore pressure model for those regions in the Delaware Mountain Group. The scale of pore pressure change across these years is on the order of hundreds of PSI, and you can see that increase over time, and particularly the increase pushing from New Mexico and down into Texas with increased deep injection in Culberson County. And then again, you see these earthquakes occurring on basement-rooted faults. Those are the black lines that are mapped here. So we also, that was one extract from the model in the Silurian Devonian, because that's where most injection takes place. And so we can look at the magnitude of pressure change there. But it's also interesting for us to look at different layers in our pore pressure model to get a sense of how geology is controlling the vertical distribution of pressures. And what we see there is, if we look at Ordovician, sitting just above basement on the left, Silurian and Devonian in the middle, and Pennsylvanian at the top of our model domain on the right, we see that we have a greater transmission of pressure downward, down section into older age units, than we do shallower into Pennsylvanian age units. And this is largely a function of the vertical permeability KB-KH ratios that are in our model. There are very few potential barriers to flow between the carbonates of Silurian Devonian age and the carbonates sitting just above basement. And so this is an expected finding that pressure is transmitting in a greater, at a greater magnitude downward than it is up. Between Silurian Devonian and Pennsylvanian, we of course have shales, including the Woodford and the Barnett, which have a little bit of a lower vertical permeability in our model than the carbonate rocks do. And so this makes sense. We expect that less pressure transmission upward. Our flow models also do a range of sensitivity studies. So we like to know how sensitive is our model to various input parameters. And there are a range of these. I'm just showing some examples here, but on the left, we can look at a porosity, either doubling or cutting in half, the same for horizontal permeability or vertical permeability, and compressibility. Those are 4 cases. What we see is that horizontal permeability has the largest impact on pressure buildup and controls both the size of the plume that we see, as well as the maximum pore pressure increase. And this makes sense because horizontal permeability is also controlling our calibration points that we have in the model, of which there are relatively few. So, this is expected that horizontal permeability is controlling both the size and the maximum pore pressure buildup. We've also looked at cases of maximum horizontal stress conditioning of permeability. It's a relatively well-known phenomenon that permeability can be increased along with maximum horizontal stress. So we looked at a variety of cases of increasing permeability to trend with the maximum horizontal stress azimuth work. And this is an interpolated map from DeVore and Zobak in 2021. But all of this case in particular didn't have a very strong effect on our distribution of pore pressure change. So one of the other things we have to do is get a sense check of how our model's performing relative to real data. One nice thing that's occurred in recent years is that since about 2018, the regulator in New Mexico has required a static bottom hole pressure data measurement prior to deep injection or prior to permitting deep injection. And so we're now amassing quite a few data points, a dozen or two, I guess, of bottom hole pressures. And what we can do is have a look at how the model is performing relative to bottom hole pressures. Now, these two, the line and the dots on this plot on the right, are on different scales, so they're actually shifted, but what I'm showing you is that the rate of change for both the model and the measured bottom hole pressure is pretty consistent. These measured bottom hole pressure data are difficult to put into a model domain because what our model shows is change over time, and what bottom hole pressures are one location and one measurement at one time. So this is kind of a challenge to calibrate. But what we do see is pore pressure increases in measured bottom hole pressures of up to about 500 psi, in some cases lower and in some cases higher. And our average modeled pore pressure increase in this region is 200 psi. So we're pretty happy that the model is performing well and capturing what's actually happening in the subsurface. Okay, so taking a look now at regional pore pressure changes, we can look at the average rate of pore pressure change or the cumulative rate. These are both in the plot on the left, with average cumulative shown as a solid line and the annual as a dashed line. You can see that across the whole model domain, the average annual pore pressure increase has started to level off from about 2021 on. And that goes with curtailments to deep injection in some areas, as well as operators just changing injection practices and backing off of some deep injection volumes. However, what we see is that the rate of earthquakes has continued to increase. It's only just now, January through March of this year, that we are seeing evidence of the rate of earthquakes starting to come down. So there's clearly a lag between injection and earthquakes, and there's also a decoupling of stressing rate, where we see the greatest increase in deep injection, and earthquake rate. So we can look now at earthquakes, start to integrate what we know about pore pressure and stressing with earthquakes, and then we'll move to integrating this work with fault interpretation work. But if we look at earthquakes in New Mexico, which we broadly characterize as being proximal to injection, almost every earthquake is near deep injection. And so these are essentially proximal earthquakes. We can sample our model at every earthquake event to pull out the modeled pore pressure change that we think that earthquake has occurred at. And you can see the distribution of those pore pressure changes now in MPa over time by year. And what we see is that the average earthquake in New Mexico has occurred at a pore pressure change of 82 psi or 0.56 MPa. So these are appreciable pore pressure changes. Many of them are higher, in some cases up to a 10% increase in the reservoir pressure of those deep injection strata. The story is very different when we look at the Culberson-Mentone earthquake zone earthquakes. And again, this is one of the most seismically active regions of the country in recent years. When we extract the model pore pressures for that region, what we see is that all early ruptures are occurring at modeled pore pressure increases that are very small, tens of kilopascals. So this is on the order of tens of psi. With the average earthquake occurring at a pore pressure change of 6.6 psi. This is a very, very small perturbation to pore pressure and effective stress. It's not out of the realm of what's been observed in other basins, in the Fort Worth Basin, for example, and I'll talk a bit more about that, as well as in Kansas and Oklahoma. But it is, again, very small. We need to know if that pore pressure change matches with what we understand about the faults in this region. So we'll just do a zoom in here and look at 4 specific faults, 2 in New Mexico and 2 in the Culberson-Mentone earthquake zone, so NM1 and NM2, CMES1 and CMES2. And I selected these faults because in New Mexico, we're closer to deep injection in some cases for NM1, a little bit more distal for NM2. Smye is the fault that hosted the magnitude 4.9 earthquake a couple of years ago. And then Smye 2 we want to look at because that's a fault with a different strike from the other three that we're looking at in this area. So what we do for each of these faults is we extract the modeled pore pressure over time that we think that fault is seeing. And so each of these are shaded by color, and then we plot the earthquake sequences, which are shaded in the same color. For reference, I've plotted in gray here the range of pore pressure change that faults in the Fort Worth Basin, the Dallas-Fort Worth area, saw when they ruptured. So there's a wide range, you know, from 0.1 MPa to closer to 1 MPa in the Fort Worth Basin. What we see is that NM1, that fault where rupture occurred in 2021, had experienced a pore pressure change that was well above any of the ruptures we saw in the Fort Worth Basin. So this is a very significantly increased pore pressure change over time. Less so for NM2, which sees more of a gradual ramp in its pore pressure state, but again, well within the realm of where we would expect to have seen that fault rupture. Same for Smye 2. Smye 1 is a really interesting fault because it's more distal from deep injection. We have a few early earthquakes in 2018, but really this sequence started to kick off in earnest in 2020. But even in 2020, our pore pressure model shows only tens of PSI pore pressure change at that fault. So there are a number of cases that we can investigate, and we have investigated in our pore pressure model. One is looking at anisotropy in the permeability field. Do we have a fracture system, for example, that just drives fluid and pressure directly toward that fault? We've looked at changes to injection rates and volumes. We've looked at changes in the compressibility field in the model, and none of them really get us to the scale of pore pressure change we need for that fault to rupture based on what we know about that fault. And so one of our interpretations from this work is that faults in this region are much more sensitive than previously understood or previously characterized, likely with lower frictional stability than assumed. So let's look at these in a bit more detail in the context of stress state. This is work by my co-author Alan Morris, and the methodology he published in a previous paper, but this work has been updated in this region with focal mechanism data provided by TextNet in the Culberson-Mentone earthquake zone area. One of the really nice ways of this work to treat stress state is to capture uncertainty. So frequently when we talk about stress, we just talk about one stress state, or we just model one stress state. What we're able to do in this work is to capture uncertainty in the azimuth of maximum horizontal stress. So these are the rows, and uncertainty in APHE or stress state, the relative magnitudes of the three principal stresses. Those are the columns. So essentially the stress state in each area can be defined by 9 possible stress tensors. The most likely stress tensor is the one that occurs in the middle, and in the center row and the center column are the next most likely, with the least likely stress states occurring in the corners. So for each of these faults then, what we can do is look at what's called the delta PFC. This is the change in pressure for a certain area of that fault to reach criticality, or for that node on the 3D fault to reach criticality. And then we can plot up the cumulative fault area for each of these 9 stress tensors as a function of delta PFC. And for reference, on each of these 4 same faults we've looked at, I've shaded the pore pressure change that our model is showing on that fault as dark gray. So you can see for NM1, with any uncertainty in the stress states, with any of those 9 stress tensors, that a large area of that fault had a delta PFC for criticality that was within the range of the pore pressure change we saw. So the pore pressure change encompasses a large range of the stability of that fault. This is an expected finding. We would be surprised if that fault hadn't slipped with deep injection and the scale of injection we've seen. With NM2, some of the stress tensors put us quite close to our pore pressure model predicting failure of that fault. The story again for Smye 1 is quite different, that in any of these nine, with any of these 9 stress tensors, this fault actually looks inherently quite stable relative to the pore pressure change that we've seen. And what we can do when we have faults with different strikes, for example, of CMES 1 and CMES 2, you'll notice that these faults are least stable with different stress tensors. So 1 through 3 make CMES 1 least stable, but they make CMES 2 most stable. And this allows us to kind of hone in on or tweak the most likely stress state in this area, which is probably 4, 5, or 6, which is something that allows both of these faults to be slipping with the modeled pore pressure changes that we're seeing. So one of these 3 stress tensors with less uncertainty in the azimuth of SH max than as characterized by these 9 tensors. Okay, moving right along, I want to finish up soon so we have time for questions. Let's look at the evolution of the earthquake sequences on these 4 faults. I think there's some interesting findings here. I'm looking now, actually just at 2 faults, sorry. NM2 is on the right, and we are looking down at these sequences in the map, in the plot on the top, so latitude versus longitude. And then we're looking with depth, earthquake hypocentral depth in the plot on the bottom. And the same for the case on the left, which is CMES 1. These earthquakes are sized by magnitude and shaded by date. So most recent earthquakes are brighter colors. So interestingly, what we see on NM2 is initial slip on this fault occurring to the northeast. And this makes sense given what we see of our pore pressure model, that those portions of the fault would be made unstable earliest. And then interestingly, in most recent years, we see another portion of this fault or another fault, perhaps a relay, that's activated at shallower depths on a different orientation than was observed for this initial portion of the fault that slipped. For CMES 1, we see migration along strike from southwest to northeast over time, as well as deepening. And so it looks like these initial earthquakes occurred more shallow section, where then we see migration of fluid or perhaps just pressure or stress down to deeper depths over time and along strike. And this again makes sense what we see of the pore pressure model, with the greatest pressure increases coming from the northwest direction on that fault. Now, I should make a note here that we don't address poroelastic stressing in this model. This is just a direct pressure diffusion model. In some of these cases, poroelasticity may play a role, but we've largely discounted that, particularly for CMES 1, because given what we know about the stress field, the orientation of SH max, as well as the strike of this fault, we would expect that poroelastic stressing with that pressure change would actually have a clamping effect on that fault and make it more stable rather than less stable. So we think that probably poroelastic stressing is not playing a dominant role here on triggering of these earthquake sequences. Okay, so one final slide on results and data. I wanted to throw this in because this is interesting new work done by our colleagues, Scott Stanowich, who's at NASA JPL, and Ann Chen at UT Aerospace Engineering. And what this is a co-seismic vertical deformation map for the November 2022 Coalson event, the magnitude 5.4. And what they've done for this is average data from the Sentinel-2 satellite from September of 2022 through January of 2023. So there are interferograms that cross that event date in November. And what I've plotted on top of that is faults interpreted by my colleague Lily Horn, and earthquakes that are occurring only in October, November, and December of last year. And so what we see is subsidence of up to 2 centimeters, in some cases even more, of the ground surface, deformation of the ground surface as a result of that Coalson event and related earthquakes in that sequence. And this is an interesting finding. The magnitude of surface deformation observed here is on par with what's observed in other areas, but this rupture is quite deep. It's at almost 8 kilometers depth. And so to see this reflected at the ground surface is, we think, really quite interesting. So there's more work to do here on modeling what's actually happening from depth to surface. So we'll be diving into that soon. Okay, so I'll stop there, but just to summarize, we've had deep injection of more than 4 billion barrels in the northern Delaware Basin into sub-Wolfcamp strata, carbonates that have inherently low matrix porosity but enhanced permeability, earthquakes in the basement, some of them large magnitude, pore pressure increases of up to 500 psi with high vertical variance due to vertical permeability differences. We have proximal triggering of earthquakes with average pore pressures of 80 or so psi, and distal triggering of earthquake sequences on faults that appear to be less stable than previously understood. So thanks very much for your time. I'll be happy to take some questions. I can see the chat here.
Yeah, thanks very much, Katie. That was fantastic. Yeah, if you have questions for Katie, please submit them to the Q&A below and she can go address them in order. So I'll pass it off to you.
Thanks. Now, am I wanting to be in chat or Q&A? What do you think? Oh, Q&A here. Okay, recording. Have you used GravMag to verify the basement? Yeah, that's a great question. That's one that my my colleague Lily Horn is working on, and she will be writing up a paper with the contributions from other people, including Owen Callahan, on basement of Texas, bringing in some of the GravMag data. Yeah, it's fascinating. If you look at particularly the inflections from high to low, for example, seem to be tracking with some of these areas of deep seismicity, all the way from the Delaware Basin into the Midland Basin and actually beyond. So the GravMag data is very valuable here for sure. Is it possible that the downward pressure transmission could be simply due to gravity? Interesting question. Of course, that it's one that we haven't really thought about and certainly addressed specifically, but yeah, I mean, you would expect, and this is pretty common, that, for example, when we look at earthquake sequences, deepening over time, transmission of fluid downward, yes, absolutely. So I would expect that locally for sure. The regional maps we're showing here, you know, shallower, the Pennsylvanian Age and Ordovician, I would say on a regional sense, I'm not sure that that would be a strong driver, but certainly locally where we have conduits, fluid conduits between the Slur and Devonian injection strata and basement. So thank you for that point. It's interesting. Next question. The majority of research indicates that injection is the trigger for seismicity. Do you have any cases of induced seismicity due to hydraulic stimulation completion of the reservoirs? Great question. So hydraulic fracturing is the main trigger in the Eagleford region, for example, and in other areas, for example, in Canada. In the Delaware Basin, that's far less of a common causal factor, but it does occur particularly in the southern Delaware Basin. So where we see that potentially playing a role, and this work is based on causal analysis that's done by Alexandros Savvaidis and Yasin Grigoratos through TextNet, where they've done spatiotemporal analyses and some more mechanistic causal analyses as well, looking at which types of operational activity may be causal influences. So there they do see a role for hydraulic fracturing stimulation. In this deep section in the northern Delaware Basin, we don't treat that as very likely, although we carry data on fluid injection for hydraulic fracturing, of course. But the main reason is that these sequences are much more long-lived. They're not the spatiotemporally isolated sequences that we would see or expect with hydraulic fracturing. They're occurring distal from operational activities, for example, in far west Culberson County. They're long-lived, they're distal from activities, and then perhaps most importantly, the faults that host these earthquakes are basement-rooted faults that don't, in most cases, extend into those strata, and the earthquakes occurring quite deep in the basement. So for a variety of reasons, in this particular study, it's not a likely causal factor. In the southern Delaware Basin, yes, to a lesser degree. Okay, next question. Did you see any trend in seismic event density and reservoir thickness of the different injection targets For disposal-induced seismicity, that's a great question and gives us a line for future research. We haven't looked specifically at this. I think there is a lot of work to do here in looking at the geologic characteristics of the injection strata themselves, and how that geology might be driving seismicity. So not specifically. I will say though that is reflected in our pore pressure model, in that the pore pressure model is not a black box model. It's based on the geology. And so if there is an effect of thickness, for example, allowing more storage capacity, more pressure diffusion, more connected permeability pathways, that will be reflected in our pore pressure model. It's a great question. Good line of research. Thank you. Next question. You model long-term pore pressure changes due to injection, but have you looked at effects of short-term injection rate on local seismicity? Another great question. So I focused today on the Delaware Basin because distal triggering is so common here in the CMES earthquake zone. We've looked at large-scale injection as the main causal mechanism. The story's a bit different in the Midland Basin, and I didn't get to talk about that today, but our group has a whole portfolio of research in the Midland Basin, and there, proximal injection and specifically injection rate and volume seems to be very important. And we can identify cases of triggering within days of increases in deep injection, particularly if we have a couple wells that are proximal to that earthquake event. So one of the things that's important here is that just recently, we have access to daily injection volumes through the TextNet injection reporting tool. This is a new requirement of the Railroad Commission just last year, and that's been extended now to deep injection in other areas. But those daily injection volumes, where previously we had just monthly, allow us to look at changes in short-term injection rate on onset of seismicity. So our set of papers in the Midland Basin will have much more of that addressed. Great question, thank you. Next to last slide, where did the engineers get their data and did they incorporate BEG, oopsies, sorry, I'm stuck here. BEG subsurface data. I am not sure what next to last slide means here, whether that's this measured bottom hole pressure data or pressure modeling. If you want to follow up with that, with which exact slide, my next to last slide is this one. So I'm not sure. Please follow up and I can answer that, or by email is fine too. Can usually cause large earthquakes. That question, I assume, we are seeing some what I would call large magnitude events for induced earthquakes. So magnitude 5.4, for example, in Coalson, that's a large induced event. It's on a basement rooted fault that cuts stiff carbonate strata and is relatively large itself. So, okay. Do you see any indication that fault reactivation de-stresses faults? They become less likely to create further seismicity with continued injection, or do faults that have seen seismicity in the past continue to slip about as easily as others? That's a great question as well. So I'm constantly surprised by how the seismicity in this Culberson-Mentone earthquake zone has persisted over time on the same faults over and over. In this case, it's a bit different because there is clearly a big role for earthquake to earthquake triggering, earthquake interactions, and stress transfer along faults. So that's slightly different from your question, whether we see faults de-stressing. I'm not sure that we've looked at that in any sort of purposeful sense. I think it's difficult because in many cases where we have earthquakes occurring, we then see deep injection being backed off on in these areas. So that's something to look into. Thanks for the question. Would it be possible to have these slides? Please follow up with me by email. We may sanitize them and share them. So my email address is public UT. Thank you. How is the initial pressure in the injection reservoirs estimated? Was it considered as hydrostatic or was there any overpressure? Great question. essentially hydrostatic is how the initial pressure is modeled. I didn't show this, but let me just see if I can get to a slide on that here for Elena. Let's see. Here's an example, if you can see this. Can you see this, Tim? Probably. Of how the initial pressure and temperature in the model were calibrated. And so just lots of data, bottom hole pressure data from existing wells in the basin with a fit to that. In this case, it's 0.46 PSI per foot. This does range we do these models in every injection area we go into and look at. And so that does vary a bit depending on stratigraphy and basin. I hope that helps. Okay, I'm gonna go back here and to the Q&A. Let's see. Oh, the co-seismic map. Okay, so the co-seismic map is the one we wanted where the engineers get their data from. If the question is about the INSAR data, this comes from satellite data that passes around the Earth, every couple of weeks, I guess, and looks at surface elevation. And therefore, when you have interferograms for different date stamps, you can, crossing the event date, for example, you can average those and get a sense of the deformation of the ground surface co-seismic with these events. As of yet, we have not tried to model what would create this ground surface deformation with an earthquake this deep. That's an area of future research. Okay, next question. With an injection and increase of pore pressure, one would expect uplift of the ground, not subsidence. How is the 2 centimeter subsidence explained? Excellent question. We have another whole area of research on anthropogenic influences and ground surface deformation. And you're absolutely right. With injection, if it occurs shallow or near ground surface, we see uplift of the ground surface. That's certainly the case for injection into Guadalupean age strata near ground surface. And in fact, we see in some cases 13 centimeters of uplift of the surface associated with that. Now, that is masked by depletion of the shales, where we see again up to 10 centimeters of subsidence of the ground surface due to depletion of the shales. And then underlying all that is deep injection. We don't at the moment think that we see any surface signal from deep injection at all. And so, if we just had deep injection, we wouldn't expect any ground surface deformation vertically. The 2 centimeters of subsidence here is specifically just with slip on this fault or these sets of faults associated with these earthquake events. And so that's just the co-seismic deformation associated with slip on the faults and these events. So we're not attributing it to pore pressure increase specifically, but slip on the faults. Okay, next question. How are the deep injection wells designed? Are they vertical or horizontal with long screens in the target zone? Most of these are, in fact, in this basin, all of these are vertical wells. Some of them open hole, some with perforated intervals, and all of that detail is taken into account in our pore pressure modeling. We are now seeing horizontal deep injectors in the Midland Basin by a few operators who would drill into the Ellenberger and drill horizontal laterals, again with perforated intervals or with open holes. Many of these wells, not necessarily just in this basin, they take fluid on a vacuum. So it's an extremely good injection reservoir, these carbonates. Is there any way to follow path of the fractures during injection stage? Good question. And again, this is an area where we're getting a little bit smarter in our workflow in the Midland Basin and trying to look at some of these more near wellbore injection effects. Looking at, for example, step rate test data and the coupling of injection rates and pressures to look at potentially inducement or creation of hydraulic fractures in the near wellbore. That doesn't tell us about directionality or path, but we have another line of research by someone on our hydrogeologic team essentially a capacitance resistance model looking at connectivity between injection wells. So looking at daily injection volumes, how those rates and pressures change over time and are coupled to one another. So that's one way where we might get an idea of that anisotropy in permeability. Good question, thanks. You have pressure change with time from your model. You could derive the rate of change of pore pressure and see if it correlates with rate of injection and see a travel time from injection to hypocenters. Yep, that's right. Absolutely, we can. And in fact, we do look at the rate of change of pore pressure, although we're looking at it annually. We could look at that perhaps as granular as monthly. And then again, this is an area where we just need more granular data. Injection rate daily data, for example, in the Midland Basin, will help us greatly there. We know from our collaborations with operators and from our experience here that, I mean, perhaps this is not a great example because some of these distal earthquakes are a function of large scale injection and general pore pressure increase. But we do know that some of transmission in some of these carbonates can be extremely fast, on the order of hours to days in terms of event triggering. Thanks for the question. Is there somewhere we can view this webinar? I think on YouTube. Regarding the INSAR, did you also look at the horizontal displacement component? Did that show any indication of fault-related deformation? Great question, Kevin. I did. We do have an east-west deformation map, and I just looked at it this morning. We don't see a lot of anything really that I can pull out as signal. There's a lot of noise in one direction or the other. The magnitude is similar, 2 centimeters east or west. I don't see anything really that looks like fault-related deformation in the horizontal displacement. Thank you. Have you investigated the effect of individual well pressure surging on nearby induced seismicity? Again, a great question. And again, I would say one that's better addressed in other basins. So many of these earthquakes are distal from deep injection. We can't target one specific well. And so we can't look at the changes in injection pressure and tie to specific faults and specific earthquakes. In the Midland Basin, we do see more cases of this where, for example, there's a 2 deep injection wells that were fairly quiet for a period of months and received a big dump of injection into both wells. And we saw a triggering of an earthquake within a kilometer of that well within a couple of days. So absolutely, that does exist. I would say that this particular natural laboratory is not the right place to address that question, though. What does the study provide on fault friction coefficients, and how well are the stress magnitudes constrained? Fault friction coefficients obviously is just such an area where we know so much less than we would like to know. We assume it to be 0.6, but through some of the work of Alan Morris and others, we do allow for that friction coefficient to vary a bit. What I would say from our work is that if our pore pressure model is accurate, sort of on the regional scale, that these faults are likely much less stable than they are assumed to be with a friction coefficient of 0.6. So we would assume that these are probably much less stable. How well are the stress magnitudes constrained? Great question. For our stress characterization, we take all available data. Again, work led by Alan Morris. There's a paper on this, 2021, Morris et al. But it gets updated continuously as we have new data. So vertical stress magnitude is constrained quite well. That's a paper I published in 2021, variations in vertical stress. And those make geologic sense, and they're constrained by density and sonic logs in several thousand wells. So that's the one we know most about. SH min, obviously we know less about, but we do have some data, engineering data, and other things, instantaneous shut-in pressures, which give us an indication of SH min. And then SH max, we just rely really heavily on essentially the AFE parameter, looking at the relative magnitudes of the principal stresses. We do have some focal mechanisms, mechanism data. So the more big earthquakes we have, the more data we have to add to our characterization of stress state. Okay, that's all I see for questions, unless anybody has any others to drop in there. Otherwise, I'll stop there.
Well, we have to end it here, but
Perfect.
thank you so much for the talk today. This talk will be posted to YouTube within the next week or so. Katie, this has been fantastic. If you have additional questions for Katie, please don't hesitate to reach out to her via email, and she will be more than willing to answer lots of questions. So,
yep. Please,
awesome
please
job.
reach out. Thank you very much.
Katie, thank you so much.
Sure. Thanks a lot.
Bye bye.
Bye all.